welcome you to this session, which is a keynote session on intelligent biomechanical machines. I am Vinod Bhanti. I am ex-chairman of ISPO India as well as Red Cross governing body member, Indian Red Cross, and I retired as head of the Department of Prosthetics and Orthotics in one of the medical colleges in India. Herewith I introduce my old friend Edward Lemaire, whom I know as, first of all, the chairman of the World Congress at Vancouver. A brief introduction of Lemaire is, Dr. Lemaire is an associate professor in Ottawa Faculty of Medicine, member of Ottawa Hospital Research Institute and Ottawa Carleton Institute for Biomedical Engineering. He is president of the Canadian National Society for International Society for Prosthetics and Orthotics, that is ISPO, and serves on the International Scientific Committee of ISPO. His talk is on intelligent biomechanical machines. I'm not taking any time or anything in between myself and Lemaire, because this system Lemaire will be presenting. Thank you very much. I hand over the mic to Edward.
Thank you very much. To start, I would like to thank ISPO for the opportunity to address the 2013 World Congress and bring up some background, current achievements, and future directions for intelligent biomechanical machines within the area of prosthetics and orthotics care. As we look into our daily lives, it appears that machines are getting smarter. Our telephones know where we are and prompt us when we're late. Our coffee makers have a fresh pot waiting for us when we wake in the morning. And you may have a robot that vacuums your house. These interactions between people and machines are important and can enhance our quality of life. But would you consider an automatic coffee machine to be intelligent? The dictionary definition of intelligent as related to machines is able to vary its state or action in response to varying situations, varying requirements, and past experiences. This definition shows that the coffee maker isn't smart enough to be intelligent, but intelligent machines that exhibit these characteristics would be excellent for enhancing biomechanical function. So an intelligent biomechanical machine should be able to recognize the current situation or environment or the action the person wishes to perform, vary the device's function to optimize the action, and learn from past performances to enhance function. Currently, we are the ultimate biomechanical machines. While other biomechanical machines may jump higher or move faster, most humans have the uncanny ability to vary their actions based on the situation and learn from past experiences. People who lack this ability likely remove themselves from the human gene pool. To achieve this biomechanical intelligence, we need to sense the environment to know what situations need to be accommodated. The human machine uses a variety of sensors that include the 5 senses, internal sensors such as muscle and skin sensory receptors. And while we work best by combining input from all these sensors, the human intelligent biomechanical machine can accommodate when sensor information is missing, such as finding your way in the dark. While we have many ways of using this sensor information, the biomechanical machine is interested in creating output as movement. While simple movements can be easily achieved, a successful biomechanical machine must be capable of performing complex movements that generate the required movement. The sensor information is needed to know what sort of movement needs to be produced. This controllability is what differentiates humans from common biomechanical machines. We have an amazing ability to assimilate great amounts of data, decide how this sensory data fits with what we want to achieve, and then decide on the most appropriate way to move based on the body's biomechanical structure. And all this happens in real time. Unfortunately, problems with the human machine are common and will become more widespread with our aging population. The field of prosthetics and orthotics, we solve problems with the human machine by introducing more biomechanical machines. And until recently, most prosthetic and orthotic devices were not intelligent. This doesn't mean that they should be considered foolish or stupid, but these devices were made to perform a specific task. And although the device function may change based on how fast the person moves, as with hydraulic devices, or how forcefully they move, as with loading a spring, no decisions are made that change how the orthopedic machine performs. Developing better orthopedic devices can make the right decision at the right time are important steps toward the next generation of prosthetic and orthotic care. The ability for a device to make a decision is an important part of an intelligent prosthetic and orthotic device. Currently, the healthcare team makes these decisions, and then a device is selected that best matches the objectives of the team and for the person. Intelligent devices would help by making some decisions based on the current situation and then adapting function to provide the optimal performance. Knowing what the user wants to do remains an elusive question for intelligent devices. Ideally, the device would react immediately after a person makes a choice. However, the reliance on a relatively small set of input data makes some of these decisions difficult. For example, it may be easier to know that you want to initiate walking from standing. It's a very abrupt sort of motion. I'm going from here to a walking motion. However, going from level ground to stairs or up a ramp or incline is a much more difficult decision to be able to make. Recent research in our lab has shown that inertial sensors, which are accelerometers, gyroscopes, magnetometers, for example, when you're wearing them, are pretty good at doing this initial sort of things or abrupt motions. When we start looking at going from, say, level ground to a slope or a ramp, there's very, very little change in the signal that you're looking at. Especially more able-bodied people, when you're walking, there's really very little change in gait. So it becomes difficult to consistently identify these activities or the user intent. So therefore, more complex sensor and analysis methods are needed to know what the person's doing at these transition points between mobility activities. But once you know what the movements that person desires to perform, the device needs to know how to perform the task. Current intelligent devices can do a good job of modifying the speed, but other aspects, such as accurate positioning of the foot or the hand, remain difficult. Also, some devices are preset for safety, which may not accommodate to the lifestyle of some people who may want to have the device act in a safer manner when they're fatigued, but allow better performance at other times, for example, during a sport or recreation activities. In terms of timing for prosthetic and orthotic assisted motion, the quick answer is you want the change to be as soon as possible. However, an intelligent device could make movement adjustments independently to maintain safety. This could include recognizing a decrease in stability and providing corrections, or opening a prosthetic hand wider as a hand approaches an object. Well, as my wife tells me, many people don't like to be told what to do. But intelligent devices of the future could help avoid or adapt to moving scenarios such as slippery surfaces, walking into traffic, or trying to perform an activity when a battery level is low or depleted. With our aging population globally, devices that help with the location tracking, safe mobility, could be beneficial to the person and society. One of the main issues, though, with these activity alarms or devices that provide independent thoughts or notification of a situation that might be dangerous. The main issue isn't accurately or providing the detecting the motion and reporting back to the person. It's false positives, the false alarms, where the device provides an unsafe warning when there really is no problem. This remains one of the biggest problems right now I think we have with almost any monitoring system, or in this case, future intelligent biomechanical machines. And what we find is that it doesn't take many false positives before the person starts ignoring the alarm, turns it off and stops using it, or they return the device and they stop using the device. Well, throughout this presentation, since it's on intelligent biomechanical machines, I'll raise various intellectual challenges throughout the presentation. In this first case, I'm making this challenge to clinicians to consider whether the prosthetic or orthotic device is making the appropriate decision for the end user. If not, can a more intelligent option be put into place? If no options are available, then the challenge is to communicate with innovators in the field to ensure that the research questions are being raised that will address the exact clinical questions that you are coming up with at the front line of patient care. Fortunately for people with disabilities, the prosthetics and orthotics field has been actively developing technologies and clinical methods that produce devices that make simple and complex decisions related to movement. In orthotics, a variety of stance control devices use mechanical or electromechanical methods to determine if the person is weight-bearing. Based on this decision, the device allows free knee motion at In orthotics, a variety of stance control devices use mechanical or electromechanical methods to determine if the person is weight-bearing. Based on this decision, the device allows free knee motion at the appropriate time. New devices, such as the Autobox C-brace, make additional decisions and then control how the knee flexes during weight-bearing. Smaller and lighter devices can be made that use mechanical systems to engage only when the leg is straight, thereby trading off more complex control for devices that are smaller and lighter, even though they aren't able to engage during a stumble or when landing with a bent knee. New hydraulic actuated control that we've been working on uses the speed of knee motion rather than contact with the ground to engage knee flexion resistance, thereby catching the person with knee extension weakness as the knee collapses. So if they land, they start to flex faster, it engages. So there are many different ways that don't require electronics that we can start to look at as well, where we're making the correct decision in a device. We are also at the beginning stages of powered lower extremity prosthetics. Both powered knees and powered ankles, let me step back on this one. In prosthetics, micro-controlled knees have been successfully implemented to control rotation. Since the knee muscles predominantly act to control motion and not to actively extend the knee, appropriate resistance adjustments needed to optimize knee function. Intelligent ankle prosthetic control has also been implemented to better position the foot when walking on different surfaces. The addition of new sensors and more intelligent software in the most recent micro-controlled prostheses has also demonstrated our ability to enhance performance and user satisfaction. We're only at the beginning of developing intelligent prosthetic devices that can adapt to the user and the environment. For powered lower extremity prosthetics, both powered knees and powered ankles are now available on the market. But the trade-off between the ability to push and the noise, the weight, and sometimes the suboptical forces, because you only generate so much force with a small and light device, make these devices a challenging choice for the consumer. These new control algorithms based on these inputs can lead us to better powered prostheses that can make independent decisions on how best to grasp and hold an object, thereby providing the enhanced function through machine intelligence as opposed to just the user defining every motion of the device. Benefit from technical and societal advances. And these factors continue to improve. The miniaturization of computing and sensing technologies drive the intelligent assistive device area. For example, there's intense competition in the smartphone market is leading to new extremely small chips that are including 3D accelerometers, gyroscopes, magnetometers, altimeters, so we can tell the change in height of your center of gravity. These are coming up in nice, small, low-power chips that we can use in our industry. I've also was researching for this presentation and found that there's fully functioning cameras, video cameras, are now 1.5 millimeters in size. I can hardly even move my fingers to 1.5 millimeters. So if we're thinking about this, there's no reason why a prosthetic hand couldn't have a camera in each finger and be able to do some sort of visual adjustments as things coming in. I mean, the technology's out there. It just needs to make the final push into the prosthetic and orthotic field. Also, batteries are more dense, and I don't mean less intelligent. The ability to store enough energy or power in a robotic, prosthetic, or orthotic device, such as a power near ankle, for a full day without needing to carry a backpack full of batteries, has been a limiting factor for everybody in this field. In the end, new approaches may be required to provide the energy we need for wearable, powered, orthopedic devices. While batteries continue to advance, we have yet to see the other possible approaches, such as fuel cells, evolve to the point where they can be used in wearable assistive devices. I know personally, I thought that we'd right now be using fuel cells when if I look back about 10 years ago and I carry a little methane bottle in my pocket and fire a little bit into my powered leg. These things, for some reason or another, just haven't made the final jump into something we can use. The new motors as well are benefiting from better materials and design improvements that reduce their weight and size. A big difference between the intelligent prosthetic and orthotic devices over the past 5 years is also the number of people wearing these devices. In addition to having the qualitative feedback on function, various manufacturers I know have been developing databases of performance and sensor data they've been able to use to continue an advanced function for the end user. Well, even though we have many devices, many factors are still in the way for achieving the ultimate biomechanical machines. Weight continues to be a major obstacle. While sensors and computing components have been extremely small and light, the machine elements that create the power and the desired motion can add considerable weight to traditional prostheses and orthoses. A trade-off is typically made between size, weight, and the maximum force or the speed of motion that's achievable. For power devices, noise is also an issue, especially since typical prosthetic and orthotic devices are very quiet. It's unclear at the moment how end users will tolerate the motor noise in various wearable mobility devices. And I know in our clinic, we've had some feedback. We had people on various powered knees and devices where the sound has been a major factor for their choice. When designing intelligent biomechanical machines, we need to remember that the case for lower extremity orthotics, the competing product could be a piece of molded plastic, which is inexpensive, it's light, and it's relatively thin. How much of an increase in function do we need before the end user trades in their current simple plastic AFO for a new intelligent device? Well, as you can see in this slide, many robotic and other devices have been developed that would have a difficult time transitioning from the laboratory to the clinic. I bring this up as a means of encouraging people who are active in prosthetic and orthotic care to engage the innovators in wearable robotics and intelligent machines. While multidisciplinary research is occurring, as we can see through many presentations here at this Congress, a disconnect often exists between clinical practice and engineering research. and bringing the day-to-day realities of living with an assisted device to the design requirement phase for research and development, I say is the responsibility of the healthcare practitioner, not just the researcher. So, how do we deal with these issues that have limited the use of intelligent, powered machines in prosthetics and orthotics? One option is the robotic exoskeleton. It's also called powered orthotics or robot suit, which is now making the transition from the laboratory to the end user, especially for the field of orthotics. In contrast to typical orthotic devices that are carried by the person, since they're attached to a limb, powered exoskeletons can be self-supporting, thereby allowing us to use heavier batteries, heavier motors in the design. Exoskeletons that are designed as a walking frame have the potential to be more stable and produce greater moments and forces than unilateral devices. However, a trade-off still exists between portability, stability, and force. Movement speed also remains an issue with these devices, and the current state-of-the-art typically delivers slower but safer movement speeds. The orthotist may be the ideal professional to fit these robotic exoskeletons, making use of their experience with interfacing the remaining limbs to the mechanical structures and in fabricating custom interfaces that could better provide force transfer to the body. However, some orthotists and orthotic educational programs may be unprepared at the moment to take on this challenge. Continuing education for current practitioners and exposure to new students can be considered another intellectual challenge that we need to meet in the future. So, while people may be attracted by the mechanical part of the machine, exoskeleton control remains a complex problem. As shown in this older video from the HAL exoskeleton developers, inappropriate powered movement and maintenance of stability are important but challenging tasks that have reached an acceptable level for some users. They remain an area that requires more research and development. Fortunately, students fall really well, so we can expect more advances in the future. Other devices that are in the pre-commercial phase, such as the Rewalk and exoskeletons, deliver pre-programmed movements based on a therapist via a controller. The movements can be triggered either by the controller or by body motion, such as tilting forward to start moving. These powered exoskeletons are currently targeted at the therapy market for use in a controlled clinical setting. But even with limited use in the clinic, being able to stand and walk brings joy to people with spinal cord injuries. And some people have reported lower limb changes, such as increased warmth and spasm relief. Another option is to control movement based on sensor and EMG, or electromyography input. The use of muscle activity signals as an input source has been questionable due to problems with the signal quality, the lack of appropriate EMG signals for people with mobility disabilities, hence their need for an assisted device because the muscles don't work appropriately. And the inconvenience of applying the electrodes every day. Implantable EMG electrodes are in development, and they may be relevant in the future for guiding robotic movements for prosthetics and orthotics. In fact, some of the things that I can't talk about that I've been a reviewer on is showing me that we're going to see implantable EMG electrodes definitely within our careers, but hopefully I think within the next 5 or 10 years on the market, which is, I think, going to be a major change in how we deal with a lot of devices. However, I would expect muscle activity for these sort of devices will only be a secondary input for system control due to the lack of reliable muscle activation for many of the people that we need the device. EMG perhaps could be a better idea as a trigger of user intent, allowing the system to better anticipate a change in activity and then use the sensors to define exactly what needs to be done. The Rex exoskeleton differs from other devices on the marketplace, mainly because, as you can see in this video, it's rather large, and they use a joystick for control. While the user in this requirement doesn't need crutches to know and user intent, they have the joystick. However, this device would be more difficult to pack up in a car. It's about 38 kilograms in weight. Not too bad, though. Overall, you see, I've changed my opinion on this exoskeleton system. At this point in the development of orthotic exoskeletons, a joystick control is likely the most appropriate and reliable method for the end user to move in the desired direction. As well, without needing crutches for movement, this allows the user to more easily perform hands-free movements. It's also interesting, it would be, to see a cashier at a local store standing and working with their exoskeleton on. However, as with other devices, continuous walking time is only about 2 hours, so continued development and strict power management by the user is also needed for the current technology to work in the workplace. You may also notice that the walking speed is relatively slow. For paraplegics, a wheelchair likely remains the fastest and most effective means of moving in their environment. So ideally, the consumer would have a mobility balance with an exoskeleton perhaps and their wheelchair at the moment for other things and other ways to move. Another approach, which is a good example of thinking outside the box, is the Honda Walk Assist. While these devices are unlike the current orthoses, they do have the advantage of a longer moment arm, as you can see in this, as it sticks from the motors are right in the back. You'll see silver kind of right behind the buttocks. This device was designed to assist movement rather than replace the movement. And in contrast to the paraplegic walking scenario, this mobility assist objective may be more appropriate for many people who require lower extremity orthotics. I'll let this go for a bit. Actually, as I said in the other presentation, she's going to stumble in a second. And she's coming up. She's doing pretty well. Whoa! Ooh, she didn't fall. I like that. That's pretty good. Anyways, I thought it was surprising. I would have thought she would have fallen over when it went back. So, based on the current state, perhaps we shouldn't be considering these as sole-use mobility devices that will replace their other prosthetic or orthotic device, but think of it more as a biomechanical docking station, where the person, I say, for those of you with a notebook or tablet computer, a docking station concept is a quick or instant connection that gives you a larger screen, a better keyboard, or other peripheral devices that improves your computing experience at your main location. The idea of an assistive docking station concedes the view that a passive or other intelligent but non-powered prosthetic or orthotic device could be sufficient for the end user for most of their activities of daily living. However, for more demanding mobility tasks in the workplace or at home, they would benefit from a powered mobility option. Efficient and effective integration between the passive and the powered machine would be required to achieve this objective, and the cost would have to be considered as with any other assistive device. This approach would expand the usefulness of the technology beyond the paraplegic walking sphere to others with lower extremity weakness. Here's a Hollywood example of using the assistive device concept. Did you notice? I put a little timer on there. 17 seconds. 17 seconds to get that device on, right? So what do we learn from the clip? Well, time is essential. People's time is valuable. And ideally, the user would be able to quickly dock to their exoskeleton, walk down the stairs, go to the kitchen, prepare some food, undock, go to the toilet, redock, go back upstairs and get dressed for their day. Hollywood may have the timing right for this 17-second challenge. And I put that out to all engineering, we need to combine engineering and orthotic principles, I think, to be able to achieve this. As a side point, the main technology in the Iron Man movie wasn't the mechanical suit, it was the power supply. Even in action hero fantasy world, they understand that without an appropriate power supply, none of these systems become viable. While intelligent biomechanical machines should also provide a viable platform for improving mobility, they also provide a viable platform for improving evidence-based practice by providing real-world outcome measures. With appropriate programming and storage, sensor-based intelligent prosthetic or orthotic devices should be able to provide mobility information to help characterize the end user, identify changes to their mobility status, or identify mechanical issues with the device. To integrate these continuous quality improvement processes into prosthetic and orthotic care, advances are needed in extracting and reporting the critical information to the appropriate person. As you can see in this image, current prosthetic devices provide a variety of sensor data that are used to determine the person's activity state. While this is essential information for the device to work appropriately, an activity report that covers the long term would be useful when arguing for funding for the next prosthetic device, and as well, could these sensors be used to determine if an energy storing foot has failed, if it's no longer providing the return that you'd want, or if another component is damaged. In addition to assistive devices, current smartphones are rich in sensors and provide a viable tool for understanding how people move outside the clinic. Research and development from our group in Ottawa is creating software on the BlackBerry platform to provide an activity profile for the end user, much like someone would carry a heart rate monitor in cardiac care. The idea is the healthcare practitioner can use this to help guide treatment, support assistive device decisions, and of course we can use it in research and development. Ideally, the consumer would be able to download a wearable mobility monitoring software onto their smartphone, put the phone on a belt holster, wear it during their day to perform movements, a few calibration movements are needed, and then wear it all day while the mobility information is logged. A mobility report could then be made available to the healthcare team. Technology is also becoming available that integrates biomechanical measurements into the environment. These include floor tiles that can measure stride parameters based on foot contact, and automated video analysis that can track falls or stumbles within elderly care facilities. For people working within a rehabilitation clinic, the potential exists for a stride parameter report to be created while the person walks from your front door down the hallway to the clinic room, and to have that report waiting on your tablet or on the computer in the clinic area to check before or during the appointment. Examples of these stride parameter measures might be stride length, walking speed, stride length, double support time. One of the main issues, though, for using device data to create usage and activity reports is access to the data or to a report. Currently, many vendors control access to device-related data, and this data remains an important competitive advantage for further development. The question, though, of who owns the data likely has different answers in different countries or different regions. Here's the question: does the end user own the data in their own assistive device? Can the user transfer proxy rights to a clinician to access the information? Is the information secure? Does the stored sensor data and its subsequent use conform to the health data or privacy laws in your country? As you can see, we're moving into new territory by trying to use this intelligent biomechanical device information to make informed health decisions. So this brings us up to the next challenge, which I'm going to call the knowledge sharing challenge. For sensor-based prosthetic devices, we would all benefit by having a way to share de-identified data or information in an open source repository. In addition to providing a means of generating specific reports that can be used by a person's attending clinician in cases where the user approves the data analysis to be extracted from their device, large data sets would allow researchers to apply complex analysis methods such as neural networks and various other machine intelligence approaches to move onward onto the next generation of prosthetic control. To continue the discussion of using biomechanical outcome measures for prosthetic and orthotic care, the topic of a quick capture and reporting should be considered. Recent discussions we had at our ISPO Canada Symposium showed that the time requirements for setup, capture, analysis, and reporting was clearly a limiting factor for using these outcome measures in clinical practice. Many cost-effective tools are available to analyze human movement, but integrating these into your daily prosthetic and orthotic clinic has been limited. At the moment, instrumented walkways might be the most viable tool for obtaining fast data collection and immediate reporting. Unfortunately, the cost, the size, or the resolution has limited its application globally. For people with disabilities, a walkway should be able to accommodate the full timed up and go test for a tall person with a wide step width. So we're looking at approximately, let's say, a 1 meter by 4 meter long at a minimum. Longer distances are preferred so we can get more consecutive foot strikes in the analysis. While current systems can provide step analysis such as walking speed, stride length, double support time, the systems are not necessarily ideal for measuring the plantar force, although the visual display of these pressures can be useful when you look at it, like, say, just visually on a footprint. The resolution in the larger walkways are really too poor to do many complex pressure analysis. For example, one system on the market only has a resolution of 2 sensors per inch. TechScan in-shoe sensors are 19 sensors per inch, and the high-resolution scan mats can be 25. So it's only 2 sensors per inch in a foot in your heel. We go longer than an inch, it's probably a difficult area to do more complex analysis. So, walkways that provide similar resolutions to in-shoe pressure management devices or measurement devices, they open the door to much more complex analysis of variability, center pressure trajectory, cell trigger frequency, loading zone analysis, so we can move beyond the simple stride parameters to be able to provide clinical decision support. Video also remains a viable tool for qualitative and quantitative biomechanical analysis. For simple video capture and playback, tablets have been largely underutilized as a means of recording patients' movements, reviewing the motion immediately, and using the video for immediate feedback to the patient. At our hospital, physio and occupational therapists are using 10-inch tablets to video the patient as the therapist walks either beside or behind them. In addition to the immediate feedback during a session, they sometimes will pull up the older video clips for comparison. And I hope you note that I said occupational therapists as well. This isn't just about mobility and motion. In fact, I think occupational therapists at our hospital were the first to really start using tablets as a feedback source for their patients. The availability of low-cost LED lights also brings up the potential to have automatic 2D movement analysis from the video recordings. To achieve this goal, a combination of technologies are required. They include intelligent video field analysis to correct for camera movement, in case you're using it from a tablet, automated detection of the LED lights in the video field, and the use of standard light placement to enable an automated segment analysis. In other words, we're going video to report automatically. But for any of these analysis technologies to become essential elements of clinical practice, the main deficit is the link from the data to knowledge. The field of prosthetics and orthotics requires intelligent software that can automatically extract the data from a variety of sources, interpret the data, analyze based on the client and the clinician needs, and deliver this data and knowledge in a form that can be used for clinical decision-making. In the end, the analysis should be applied to inform or change practice. The desire to use information to actually change your initial decision regarding a patient can also be an obstacle. I remember a conversation I had early in my research career where we had a diabetic foot study going on. Where we're starting it, we're going through the methods, and I asked the primary clinician on the project, saying, great, when we do this, so I guess if it's this other option, I guess you'll change the way you practice. And he said, no, I probably won't. I said, well, why are we doing this study? The whole purpose is to know what's going on. You're not even going to change the way you practice if I tell you that this other way works and yours doesn't. So this kind of triggers this in my head, that application of the evidence is really the strongest enabler. If we don't have the evidence applied, we aren't going to have intelligent biomechanical machines out there. So this brings us to my next one, the data to knowledge challenge. This challenge requires a balancing act between the speed, precision, and quality. For the process perspective, biomechanical analysis systems need to evolve to provide setup and data collection in minutes or seconds, provide the relevant reports immediately with no delay immediately after data collection, and include intelligent error checking to improve the data quality. On the quality side, new methods are required that recognize unusual outcomes, flag outliers in the information, improve the data quality. Application-specific reports that help focus the interpretation and provide information on the context of the outcomes, such as how the outcome deviates from other people with the same condition, are needed. This knowledge from data can be used by the healthcare provider, but also to empower the consumer, enabling them to understand the clinical care path and possibly help with funding devices in the future. But in the end, you must use these tools when they're available. Practice evidence-based practice. Create the evidence. Assess the evidence. Use the evidence. Share the evidence. Be the evidence. Well, maybe the last one was a little bit too much, but you can take the first 5 and go move with them. So to conclude this journey through the topic of intelligent biomechanical machines, I reference this image that states, "The world is in the hands of technology." I thought this was a fitting phrase for the field of prosthetic and orthotic care, where technology can be an enabler to help people regain control of their world. We work in a field where technology and people meet intimately, although in contrast to Michelangelo's The Creation of Adam, that's on the ceiling of the Sistine Chapel, it's man who gives the spark of life to the machine. In the end, it all comes back to the person. Thank you.